All right, so on Tuesday, we were talking about how when you rotate, or not when you rotate a shape, we're looking for basically the area between two curves. The reason that's so important is because what we're going to start looking at tonight is how to find volume. And if you remember from your geometry classes way back when, the volume of any shape is the area of its base times its height. So we have a cut cylinder here. So if you find the area of the base times the height, I'll get you, or a circular cylinder, the area of the circle on the bottom is pi r squared times the height. Rectangular box, length times width will give you the area of the rectangle, and then you multiply it by the height to find its volume. The problem comes in when we get some crazy shape like this that changes over time, and that the base isn't something that I can easily calculate. So it's like, okay, how do we figure out the area for a shape like that? That's where calculus comes in. So if we basically, what integration allows us to do is to cut it up into a bunch of little slices. And if we find the area of each of those slices, we can find the area of the entire shape. Integration allows us to take those slices and make them infinitely small. So that's basically what we're looking at. You're looking at the integral of the area of that shape over the range that you're looking at, because that ends up making it your height. So the formula, or the volume formula for it, is just the integral from A to B of the area of that shape, of the slice. So it's actually pretty simple to find using the integration. All right, so let's look at a couple and see how it actually ends up working and everything else. So if we look at the example 2 right here, so we've got our curve. Our curve is y equals the square root of x. That's the curve. And we're rotating it around the x-axis. Now, how you're rotating it is actually going to matter, because when we're looking at this method, we're going to look at 2 methods tonight. And this method, if you're rotating around the x-axis, you want it solved for y. So it's y, or in terms of x. If you're rotating around the y-axis, you want it in terms of y. So this one, it's in terms of x, and we're rotating around the x-axis. So you can see this is the actual shape that we're going to get when we rotate this curve around it. So I'm looking for the area of this slice in that. All right, so the area, A of x, that slice is a circle. So the radius, so if we think about a circle, my area of a circle is pi r squared. So I have pi, and my radius is the square root of x squared. So as you can see right here, that's the radius. And if I rotate it around, that's going to make my entire circle. So to look for the area of that circle, it's pi times the square root of x squared. So that would make this just pi x.
Excuse me, Professor. On the top left figure there, we haven't gotten to how to do that yet, right? That's just the definition.
Oh, we're not actually going to do that shape.
Okay, we're not there yet.
No, they made a crazy shape just to say, here, look, this is what we could do. No, we're not actually going to find the volume of that shape. You could, if they gave us the formulas for it, which they don't in this book. So
thank you.
No problem. It was like one of those examples, like, yeah, see, oh, these are easy. All right, let's find a hard one. All right,
now,
so we've got,
is this going to be on the test? That's what you're telling me?
Yes, exactly. Yeah.
Ah.
No, actually, I will tell you, I'm really good with my tests. If I'm not going to, if I don't go over something in class, it's probably not going to show up on a test.
Yeah, that's what I hate about Calc 1, because you do the simple ones in Calc 1, and then somehow your test was like integrating 5 different applications at once, and I hated it.
Yeah, no, I'm not that type of person. I'm pretty sure, and honestly, when you probably the beginning of next week, I'll probably have it up there. I'm gonna have the practice test up there, so you're gonna see exactly what's on the test before you even take the test. So, and if you have questions on the practice test, we can go over those. I have a review day built in, so it won't be a problem. All right, so we've got the area. So now all I have to do is the integral of that. So it's just going to be the integral from 0 to 1 of pi x dx. Which is pi x squared over 2 from 0 to 1. So this, actually, I'm going to put it over here because I'm running out of space. So the area or the volume is pi over 2. You just plug in the 1 and the 0.
Oh, Professor, why isn't the two of the 2 pi r in there? Why is it just pi x again?
Because the squared and the square cancel each other out.
Oh, okay. Wait, maybe I'm stupid. Wait, that doesn't actually completely make sense to me. So normally it would be no.
So your area is pi times radius squared.
Yep.
Your radius in this case, actually, let's not use blue, is right there, which is the square root of x. So that's
Okay.
your radius. So
Oh gosh. Okay, got it.
Square root of x squared, which cancels it out.
Thank you.
That's actually, honestly, out of this one in this problem, the integration is not going to be that hard. Looking for the area and getting the area to be correct is probably going to be the hardest part of this, because like in this case, you have to simplify it down or stuff, and in more complicated ones where we have different pieces, you have to do a little bit more work to find the area of what you're looking for. The nice thing is pretty much all the shapes you're going to do, you're rotating, which means they're going to turn into circles. So the pi r squared is pretty much what you're going to use to do that rotation. And then it's just a matter of what the radius is of the shape. All right. Any other questions with this one? Or go on to another one? All right. So this one, they gave us the equation y equals x to the third. And we're looking from y equals 8 and x equals 0 or y equals 0, actually, in this case, because it's the same value. And we're rotating this one around the y-axis. All right, now that's important because if we're rotating around the y-axis, I need my equation in terms of y, not in terms of x. So for this one, I need to change the y equals x to the third. I need to change this to the cubed root of y equals x. So I need to solve it for x to get it in terms of y. Does that part make sense? Why we're doing that?
Because we have to solve for x.
Yeah. So because in this case, since we're rotating around the y-axis, I need all my equations in terms of y. So it has to be x equals, so it's the function of y instead of the function of x. So now we're looking for my area. So again, it's the same thing. It's pi r squared. So it's pi times the cubed root of y squared. Which, if I simplify this down a little bit, it's y to the 2/3. No, that should be y, it's not x's. Now we're going to do the exact same thing. So we're doing the integral from 0 to 8 of pi to the 2/3 dy. So we're going to add 1 to that. So I've got pi to the, actually, yeah, we'll leave the pi. So it's 3y to the 5/3 over 5. And we're evaluating that from 0 to 8. All right, any questions with that part before we just do the actual evaluation of it?
Where'd you pull the 3 from in front of the Y?
It's the cube root.
Okay.
So, so that 3, it comes, because remember, you take whatever the exponent is, and you're dividing by it. So since we're dividing by 5/3, you end up flipping it over.
I see.
All right, so now we can do the nice thing is the 0 is going to cancel out, so I don't have to worry about the 0 one. So I have the cube root of 8 is 2, so 2 to the 5th power is 32. So I have 32 times 3, which is 96 over 5. So it's 96 pi over 5 is my volume for this one.
And it's all right for us to leave our answers just like that?
Yep, exactly like that. I actually, this is one of my little things. I actually prefer it like that than as a decimal. Decimals are nice, except you have to round so they're not exact. And I found that a lot of people have a tendency to screw things up when they switch to decimals, and it's not as useful when we're moving forward. So you're going to notice, especially in trig, if you change things down, sometimes it's actually easier to leave it like the square root of 2 over 2, because when you're using it, that simplifies easier than 0.707 da 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 out. So it's actually easier to work sometimes with the actual rational or the rational numbers instead of a decimal answer.
Gotcha.
Now, when you're doing a real life situation and stuff like that, or dealing with money, rounding it to 2 decimal places, it's fine when you're going out. So just a matter of what the situation calls for. All right. Now let's do one that's a little crazier. So you've seen the basic concept when it's rotated. Notice each of these only have one shape. So we're just taking that one and rotating it around. We did it around the x-axis. We did it around the y-axis. Now we're going to take a shape that's actually made up of 2 equations and rotating it around. So you notice this one, we're taking this shape over here. So we're taking this little curve right there and going to rotate it around the x-axis. And what that's going to cause is it actually causes a hole in the middle of the shape. So when I'm looking for the volume, I don't want the volume of the whole thing. I only want the volume of the actual shape. So that hole's got to come out of it. So this is where I was saying that the area kind of gets a little more confusing, because now we're not looking at just one line for my area. My area actually is between those 2 equations. So we have to do a little more calculations for it. So they did give me the 2 equations. It's y equals x and y equals x squared. They're both solved in terms of x, so that's good. We're rotating around the x-axis. So we're going to look at a to the x. So if we're looking at my radius here, we're looking at just that little line right in the middle there. So the bigger of the 2 is the x, and the smaller of the 2 is the x squared. So I have pi, the first one is x squared, and then minus pi x squared squared. So we have pi x squared minus x to the fourth. So remember, whenever you're doing this, just like we did in the last section, you want to take the top one minus the bottom one.
I'm confused how rotating those shapes creates a hole.
So this is the hard part. You kind of got to visualize it because there's no way for me to do this. All right. So if you're going to take this and flip it over to just the other side. All right. We have, let's see if I can actually draw this a little better. No, that's not drawing it a little better. That's
Oh, a hole that would have the x-axis running through it?
yeah. So basically this piece right in here ends up being the hole because we're going to rotate it around that. So there's no actual space there because that's not colored in.
Okay, the donut, the pink donut that it's showing us is our approximation. That's our delta x.
Yes. Yeah.
Okay, that's
So this
That's right,
right
that's
here
correct, yeah.
basically is what it looks like, and that's going to get bigger or smaller depending on where it is in the actual shape. So you have the hole in the middle that's would be going down to a single point at 0, 0.
gotcha.
Yeah, as I was telling because I'm actually doing volume with my high school geometry class today, and we're looking at three-dimensional shapes and stuff, and they're trying to figure out how like cross sections and stuff like that. I'm like, yep, and now you have to learn to visualize 3 dimensions on a piece of paper. And yeah, it's not always the easiest thing in the world to do.
So that makes like a funnel.
Basically, yeah, it's almost like like the old horns from their like speakers stuff. It's kind of like
Okay.
it's funneling into that point. Yeah. So all right, so we've got. So now do you see how we got the area piece from it? Because I got to subtract those 2 parts off.
Could you just explain the area piece, like why we have to subtract them like that, or?
All right, so because basically, if you're thinking about it, I'm gonna actually make this shape a little bigger so I can draw a little better on it, and then I'll change it back. So if I'm looking at just the x, when I'm looking at that line, it's going all the way down to the x-axis. So if I'm just doing the area of the y of that, y equals x, if I'm looking at just that one, I'm going to find that line all the way down to the x-axis. But I don't want it all the way down to the x-axis. I want to stop it at the y equals x squared. So by finding the x squared one, that's going to give me the area all the way down to that point. So I want the space between them. So that's why I'm going to subtract those 2. So in this case, I'm subtracting the x, or the red line, because that's going all the way up. I'm subtracting the green line from that red line to get just the little piece in the middle that I actually wanted.
All right, thank you.
No problem. I know when you look at it, it looks really counterintuitive to be thinking x squared is going to be bigger than x to the 4th. But if you remember, when we're doing it less than 1, it ends up becoming less than it because it's all fractional points at that point.
So could you say that one section of that would be the thickness of the cone?
Yeah, so that blue space right here in that first shape over here that's colored in, that's the thickness of that cone. That's the thickness of the side.
Okay.
So, and we're looking for the space between it because that's actually what we're looking for is in terms of the volume. All right, so we've got our area. So now let's just do my integral. So it's the integral from 0 to 1 of pi x squared minus x to the 4th dx. Remember, you can always pull out any constants, so the pi can just go out in front of it. So I really don't need to worry about the pi in terms of this problem. So it's pi, and then we have x to the 3rd over 3 minus x to the 5th over 5. And we're evaluating this from 0 to 1. So I've got pi 1/3 minus 1/5, which is 2 pi over 15 is my volume. Any questions with that one? Do one more crazy shape. All right. So if you're looking at this one, again, we've got two different lines in this case. We've got y equals x and y equals x squared. So very similar to what we were just doing a minute ago. Same actual equations. The only difference is instead of rotating it around the x-axis, I'm going to rotate it around y equals 2. So we're in essence shifting the rotation point up by 2 places. All right. So that's going to change my radius of my circles. And that's the piece that's the important part is, remember, whenever we're looking for area, we're looking for, we need is pi times radius squared. So I need the radius. So when we look at this, they kind of did it out nice over here with the, when they cook out one of the donuts. So if we're looking at this, I'm looking at this line right here. That's where I'm going across. So when we're going up to that point, my line inside, so was that y equals x line. So the y equals x is that line going up. I'm actually going to do 2 minus x to get the radius of that curve. Because it's 2, I'm basically taking wherever that is and subtracting off that line to go down to, so it doesn't go all the way down to the x-axis. Does that part make sense or no?
I'm sorry, I'm not sure I follow.
All right. So, actually, I got a better way to do this. So I'm taking this point right here. Actually, I'm going to put that point there. All right, so I'm taking that point right there. That y, so that's on that thing. And I'm going to rotate it around the y equals 2 line. So at that point, I need to know what the radius is. So at that point right there, my radius is 2 minus 1. Okay, because I'm looking at the line. So I can draw it.
Because the line starts at 2 and the point ends at 1.
Right. So for this one, I'm looking to find the radius from this. So at this point right here, my radius is 2 minus 1. Okay.
Yep.
At this point right here, my radius is 2 minus 1/2. So in essence, my radius for this one right here, no matter where I'm going to be, is 2 minus whatever the x value is. And I'll be right back. I got something in my eye. All right, does that part make sense? On why we're doing that?
It wouldn't be 2 minus 1.5 there. It'd be 2 minus 1/2.
Yeah, because I'm at right that point right there would be point, it'd be 1/2 up because that's one, that'd be halfway.
Okay.
Actually, I think I'm a little off. I think half actually is a little bit over, but you get the idea in that respect. So that's why that radius is 2 minus x, because I'm looking at from that red line down to the blue line. Okay? Because I need it over that entire range. So I'm not just looking at one point. I'm looking at it from every point from 0 to +1. Now the other equation was y equals x squared. So we're going to do the exact same thing on this one. Is I'm looking at this radius from that purple line up to the red line. So this one is going to be the same thing. It's going to be 2 minus x squared. Does that make sense?
Okay.
Okay. So the same concept's going to come up into there. So take that. And I'll put that one. So what I end up getting is the blue one is to there, and that's 2 minus x. The green one is all the way down to there, and that's 2 minus x squared. So those are the radiuses. If I was to spin it around that line, that would be the radius of those circles. So if we look at the area, let's look at the area of the blue for a second. So that one's going to be pi times 2 minus x squared. That would be the area of that blue circle if I was to rotate it around. And the area of the purple is pi 2 minus x squared. Does that make sense? That's what I was saying. The hardest part of this is literally trying to figure out the area and where you're rotating and where you're curving and what the radius is going to be for those different shapes. And it's not hard when it's just one around the x-axis, but when we start adding multiple and shift them around, it becomes a lot more complicated. All right, so if we're looking at this now, if I'm looking at for the area of x, so I got to find the area of this whole, the actual whole piece in here. So I'm looking basically for this piece. That's what I'm looking for, is that piece right inside there. So the question is now which one, so how am I subtracting these two? Because I've got two equations. So which of the two equations is going to go first? The purple one or the blue one?
The purple one?
Right, because that's the furthest one away from where I'm rotating. So when we're rotating, that purple one is in essence on top. So I'm going to have pi 2 minus x squared minus pi 2 minus x squared.
So in this case, we're because the axis is just rotating around the 2, where the x, whatever the x line that goes across the y equals 2, does that mean, is that why we are taking what would normally be we're just effectively just xing out the inner line, right? The inner, that's the whole.
Right. So in essence, so normally the concept we're doing it before around like the x-axis stuff, we said whichever one's on top, we would subtract. The other part we would subtract. So when we were rotating this exact one around the x-axis, it was the x line minus the x squared line because the x line was on top. But since I'm not rotating around the x-axis, since I'm flipping it up, when I go up top of this one above that line, the x squared actually would be on top. And the x would be on the bottom. So it's in essence, when you're looking at it, it's whichever one's closest to where you're going is where the subtraction, that's going to be the subtracted part. Because that's going to make the whole.
So we just have to think about the proximity to the point of rotation.
Exactly. Yep. That's a good way to think about it. All right. So my suggestion when you're doing this is clean up your area as much as you can before we go to do our actual integration. So we're going to clean this one up so it actually works out nice and we have the thing. We can pull the pie out so you don't even have to really worry about the pie part. So we're literally just going to foil out these pieces. I'll tell you my biggest pet peeve in the world. That's not that. And it's crazy. Like everybody's gonna go, yeah, duh, that's not what that is. I see that on every single year I've ever taught this class. Somebody does that on the test. Okay. Remember, when you're having a square, it's FOIL it. You have to multiply it out. You're going to have a middle term. So that does not equal that. And I really think it's not that people don't remember that that's the case. It's just you're doing things quick and you just square it and you forget that you actually have to do the middle terms. So this one we have 4 minus 4x squared plus x to the 4th. And then we have minus 4 minus 4. Plus x squared. So we end up getting pi. And we have x to the 4th minus 5x squared plus 4x. Final simplification. Another little thing that people always screw up. Don't forget to distribute the negative sign to everything. So that becomes a negative 4, a positive 4x, and a negative x squared. This is why I was saying last class, in the first class, it's the majority of your mistakes are not going to be the calculus. The majority of your mistakes are going to be algebra things just like this. Just like the majority of the algebra mistakes my kids make, or not algebra mistakes, it's arithmetic mistakes. All right. Any questions on this before we actually do calculus? Considering so far nothing that we've done is calculus in this problem.
I'm ready to do some calculus.
All right. So now we're going to do our integration. So we're integrating this from, was it 0 to 1, I think it was? Yeah, 0 to 1. And then we can just pull out the pi, just put it out in front, so this way we don't have to worry about it. So we've got x to the 5th over 5 minus 5x to the 3rd over 3 plus 4x squared over 2, 0 to 1. So we've got pi 1/5 minus 5/3 plus 2. So it ends up equaling 8 pi over 15. And out of this entire problem, that was all the calculus.
Oh, I actually do have one question. I forgot to ask about this before. What happens to the exponents after you do that? What happens to those?
When I went to here,
Yeah, like when you went to there, what happens to them?
oh, all I'm doing is I'm plugging in 0 and 1. So since these every term has an x in it, the 0 basically just cancels them all out. So I don't even have to worry about the 0. And 1 to the 5th power is just 1. 1 to the 3rd power is still 1. So that's why the exponents kind of disappear in this one. If it was
Oh,
0,
you're plugging.
you'd have actually seen the exponents used because I'd had to do 2 to the 5th power. So
Oh, I understand now. Okay.
no problem. Yeah, I can see how it's like, where did everything go? I mean, it was a decent question. All right. Look at this. So we've got this curve. And I want to rotate it around the y-axis. So we're going duplicate. Let's see if I can flip. Ah, darn it. No, that's not quite what I wanted. It doesn't have a flip option. Oh, so I basically want it over on this side over here. That's where, so I'm rotating it around the y-axis. So the question is for me to do that, I need to find the length of that line to find the radius. But I don't know what the left and the right sides are because it's the same equation. So we're looking at it as like, okay, the method that we have looking at disks just isn't going to work for a problem like this. So we have another method we can use. So the method you just learned, the one that we just did, this method, this wonderful method over here, this is known as the disk method because my shapes are all end up becoming disks. The next method we're going to look at is known as the cylinder method. So in the cylinder method, we're basically making cylinders. So we're going to cut the shape up into a bunch of cylinders to find the volume. Now, when we're looking at cylinders, we don't have this necessarily area anymore. We actually have volume. So remember the formula for volume of a cylinder is the radius, or not the radius, the circumference, which is 2 pi r, times the height, times the thickness, basically, of it, which in this case we're calling pi r, or change in r. So it's actually how thick the shape is. So because if you actually looked at it in this case, or the volume would be 2 pi r squared times the height. So, but remember, my radius in that cylinder is actually what's changing in the problem. So my radius is what's going down to 0 in this case. The circumference isn't changing, the height's not changing, my radius is changing to 0 in this case. Where in the disk, the radius wasn't changing, it was the actual thickness of the disk that was changing, and that was going down to 0. So my formula for,
Professor, could you please repeat that part?
yeah, so when I was looking at the disk, when we were looking at the disk, the thickness of it was what's going down to 0. So that's why I didn't have to worry about how thick that disk was, because that's what the dx at the end was taking care of. I was just taking the area and multiplying it by how thick it was, which was going to nothing. When we're looking at a cylinder, in this case, if we're looking at this, I can make this one a little bit bigger. If we're looking at this, the cylinders, the height is not changing over the height's my actual function. So that piece is there. The radius is how wide the cylinder is. So I do still want that. I want the circumference to know how around the edge of that shape. But the thickness on how thick it is, that's what's getting smaller and smaller if you notice in these shapes. So that is my change in R. That's going to be my dx basically at the end, because that's how thick the actual shape is. So if you want to think about it in real life terms, if you think about a soup can, the can of soup's big, the label is a slice. That's what we're actually looking at. So we're looking at not the actual can, we're looking at that label that's around the can. And as you can see, that's a really thin piece. Think about it that way, it's as that's getting thinner and thinner, that's what we're looking at. So if we find that, the volume of that shape, we're going to be able to, if we have multiple of those, we can find the volume of the whole shape. Does that make sense?
So in this case, the radius is like we're Xing out the whatever the hole is in the middle there from the bigger circumference, right? That area, and then
So in
the
essence, my radius is no longer existent in terms of the calculation. The radius is just always going to be X in terms of the problem, or Y if I'm going around the other direction. So we're not going to be looking for the radius anymore in this problem, when we're doing this cylinder.
So the height is, or whatever the function of height is, what's going to contain the variable.
Correct. The height is what we're actually looking for. That's the piece that's the actual important part in terms of the cylinder, in terms of the cylinder method.
Why is there so in the definition there it says 2 pi x f of x?
Right, because the X, it's always going to be X. My radius is always going to be X because that's telling me how far away from the middle I'm getting. So if we look at, it's actually, I'll zoom this one a little bit more. So if we look at this one right here. So I'm looking at this slice right here, or this cylinder. So my radius is from the middle out. That's X. It's from the y-axis out to wherever I am. So that's, the radius is always going to be X.
Mm-hmm.
My circumference is always going to be pi 2 pi x, because that's always going to give me my circumference.
Okay.
The piece that's important is my height, and that's my function that I got. That's the f of x. Because that's what changes over time. If I get a little closer, it's still x, but the height's a little higher now, because that's the function is a little higher at that point.
Now, what if, like in the last problem, we rotated around something other than the origin?
that becomes tricky.
Because then it would be our radius, it would be X plus 2, let's say, right?
Correct. Your radius would actually change in that situation. Let's see if I can find one. Yeah, I can do one of those. We'll do one before the end
Okay.
so you can see it. So you're right. When you're doing that, since we're not rotating around it, in that case, the radius is going to change, not necessarily the height piece of that one. So yeah, but I'll actually do one of those so you can see one. I didn't have it planned, but that's fine.
Sorry.
No, that's fine. That's like, I never worry about those things. I'm one of those weird teachers that don't sit there and plan out my entire lesson to have it all done up and say, oh, here's all the problems done. I literally do them out with you. So sometimes I'm going to totally make a mistake, and that's okay. All right. All right, so let's actually do one. Oh, so that's actually, because I didn't actually tell you this. I know everybody saw it. That's the actual integral formula. So it's just 2 pi x times f of x. So actually, if you're thinking about it, we were talking about before, the 2 pi, it can just come straight out. So you don't have to actually leave the 2 pi in. So it's really just f of x dx. Now, here's the other thing. The problem that's on the screen, we're rotating around the y-axis, and it's solved in terms of x. So if you remember in the disk method, I said whatever we're rotating around, it has to be solved for that. So if we're rotating around the x-axis, it's solved for x. If we're rotating around the y-axis, it's solved for y. It's all or solved in terms of y, I should say. And this one, it's the exact opposite. If we're rotating around the y-axis, we want the problem solved in terms of x. If we're rotating around the x-axis, it's going to be solved in terms of y. Okay, so it's the opposite method or the opposite connection. All right, let's do one. All right, so we've got this problem. So we want to have this shape rotated around the y-axis. So I've got y equals 2x squared minus x to the third. And we're rotating around the y-axis, and in terms of my bounds, it's 0 to 2. So all I don't need to go through and figure out the area or anything else on this one now. And this one doesn't have anything crazy in it in terms of how it's moving or if there's multiple ones. So we have my integral from 0 to 2. I'll pull my 2 pi out so I don't have to worry about it there. I have x times 2x squared minus x to the third dx. And let's solve it. Oh, actually, let's clean this up a little bit. So, I don't know, like, I know some teachers want you to rewrite everything completely out. You don't have to. I know you're not going to do this all in your test, so it's like, it's easy. That becomes that, so I don't have to rewrite the integral out and all that other stuff. So I have 2 pi. So I've got, what is it? 2x to the fourth over 4 minus x to the fifth over 5 from 0 to 2. Pi.
Hey, Professor, how did we get to 2x3 minus x4?
I just distributed the x.
Oh, wow. Sorry.
That's okay. I did it quick, so it's fine. And I don't think I actually said I distributed the x. I just wrote it. So plug in the 0 is going to cancel everything out, so I don't have to worry about that one, which is good. Plug in the 2. So this is 8 minus 32 over 5. So I end up getting 16 pi over 5 is my volume.
Professor,
So in this graphic, in this figure, it's a little confusing because we're only rotating the cylinder north, or the only volume, I guess, that we're worried about is the area. Sorry, is it the area south or north of the curve?
You're finding the thing that you're rotating is this. You're rotating that whole thing.
Sorry, are you pointing at something? Okay. Oh,
It's
there we go.
drawing. Okay. So I draw on a tablet, which is actually a separate computer, so it's actually connected to this. So sometimes it doesn't instantly go. So yeah, so you're rotating that shape around the y-axis.
Okay.
That's what you're finding the volume of.
Is it? Oh, okay. So
They
oh,
just
right.
gave
So
you
the height
one-
is changing.
Huh?
Right. So that's where the height is changing.
Correct. Yep.
So, and if we wanted to rotate it around, let's say we wanted the shape formed by rotating it around the y-axis, would we just solve it all for y and do it?
Yeah. So actually, this is a great example of this. If you were to rotate this around, actually, let me do that. That's a good question. Duplicate. So if I was going to do a y1 in a minute, and we're not going to end up solving this one because you actually can't. If we were going to try to rotate this around the x-axis, I would have to solve this in terms of y. So my problem is y equals 2x to the, or 2x squared minus x to the third. I have to get x by itself to do that. So probably not going to be the easiest way in the world to do it.
and you said this is opposite from the other method, the disk
Right.
method. So in the disk method, if we rotate around the y-axis, we solve for x.
Correct.
And here, when we rotate around the y-axis, we solve for y.
Correct. So in this one, actually, if you wanted to rotate this one around the x-axis, I would do the disk method because we know our radius. So I wouldn't try to do the cylinder method if we're rotating around, if we were going to go this direction with it. I would do the disk method. So that's why some people look at it as like, oh, like we went back to this problem here. This was actually way easier than what we did with the disk method in some of the problems. All right, because we didn't have to find the area, there was anything there, it was just plug in and we were done. So some people are like, oh, I always want to use this. This is why there's two methods. One method is not always going to work. There are certain problems that you'll be able to do both methods for, and they'll both work. One will be easier than the other one, but they'll both work. And actually, I was going to do one of those problems. But there's some situations like this where you can't do the cylinder method with it. Because in essence, why would we be looking at the cylinder like this? That's the cylinder piece that would be rotated around. And notice how I don't know those two sides because it's the same equation. So it's actually the exact same problem or the opposite of the problem that we looked at originally with here. I can't use the disk method when I'm rotating around the Y because I don't know those two sides. So that's why we have two methods, because each one of them has its use cases for it. Does that answer your question in a really long, drawn out way? All right. Let's look at one that has multiple equations. So this one has a hole, which is fine. Nice thing is they gave us both sides, you can see it. We're rotating this around the y-axis, so we're going to have them solve for x. So in this case, we're looking for my shell height. That's the piece that I need to know. The rest of the equation basically stays the same. So if we're looking at this, remember, we're basically looking at this little line right in there. Okay. And that line is between the x and the x squared. So I'm just going to subtract those two equations. So when we're looking at my volume formula, so it's the integral from, was it 0 to 1 in this case? Yeah. If they don't tell you which ones you're using, you're looking at the intersection points. And these intersect, that's at 1. And that's at 0. That's how I got the 0 and the 1. So I've got the 2 pi x, that's my circumference. And then my height in this case is x minus x squared dx. So
That's actually pretty easy. Then.
yeah, it's not, it's almost like if you're thinking about when we did the disk method, that's my radius. It's in essence the same concept. So it's just looking at the height of that cylinder at that point. And now we can solve it. So I'll pull out the 2 pi. It's going to go from 0 to 1 of x squared minus x to the third. So x to the third over 3 minus x to the fourth over 4 from 0 to 1. So this was 1/3 and 1/4. So I end up getting pi over 6.
These have all been nice because we don't have to evaluate the 0 because everything kind of cancels easily.
Yeah, they give you nice little problems where that's canceling out nice and easy.
So what happens when they don't? We end up doing the subtraction.
Yeah, you just have to do the subtraction. That's
Okay.
it. They actually do a little bit nice when they're doing most of these problems. They're using in terms of the x equations. The only times that you're going to have situations where the 0 wouldn't cancel out is if you have e to the x. Because right now we're not doing any real complicated integration. So at this point, you're really only going to have e to the x and maybe like sine and cosines and stuff in there that might have the zeros. So it's not going to be anything majorly complicated. That they say for chapter 7. All right. Now, you wanted one shifted, which is fine. Oh, yeah, I'll do the shifted one. I'll skip that one and do the shifted one. There. All right, so this one we're going to find the volume of a solid by rotating this region around x equals 2. So what we have is this. So this is my shape, and we're rotating around x equals 2. So that you end up getting this little arc. Horrible little arc. This little arc right there, and that little arc right there. That's what actually ended up getting rotated around. So when we're doing this one now, we have to figure out. So the thing that's going to change is the radius. All right, that's the piece that's going to change. So I have my volume equals the integral. We're doing it from 0 to 1 in this case. I have 2 pi. We're going to leave a space here. Now my height is set. That's just x minus x squared. So the height's easy. That's just my f of x. The radius is, we're starting off at 2. So we still have the x, but it's going to be 2 minus whatever x is. So if I'm right at this point here, it's going to be 2 minus 1. If I'm at this point right here, it's going to be 2 minus a half. If I'm at this point right here, it's going to be 2 minus a quarter. So my radius is 2 minus x in this situation. So in the last one, what changed was not the height, or the actual x value in it. So we had actually subtracted everything else to figure out the difference in the heights. In this case, it's the radius that changes. So it's not just x because we're shifting it off the x. Does that make sense? And again, since we're still rotating, in essence, around the x-axis, even though it's around x equals 2, we're rotating around a vertical axis. You still are solving for x. If you're rotating around a horizontal axis, you need to solve. Yeah, but in terms of y. All right, so now this one, we actually do have to FOIL this part out. We'll pull out the 2 pi. When you FOIL this out, we end up getting x to the third minus 3x squared plus 2x. So we got 2x minus 2x squared minus x squared plus x to the third. And the other nice thing about a lot of times when you're doing integration, because your constant term always ends up going up to x, when you plug in 0, it kind of cancels out even if you have a constant term in it. So. So we have x to the 4th over 4. Minus 3x to the 3rd over 3 plus 2x squared over 2. We're doing it from 0 to 1. 2 pi 1/4 minus 1 plus 1. So it ends up equaling pi over 2. I'm going to do. All right. I didn't want to go off. Because I haven't done one around the x-axis, and I want to do that one.
So if we want that answer guide for 6.1 and 6.2, you want us to email you?
Yeah, just send me an email and I'll reply to you with it. It's just a PDF file. So I can't post it up on my website for everybody, so that's because I get in trouble. But I can email it to you, nobody would know.
Cool. Thank you.
No problem. All right, one more. Because I do want to do one around the x-axis. All right, so we've got this equation. We've got y equals square root of x. So now this time we want to rotate this around the x-axis. So that means since I'm rotating around the x-axis, I need it solved for x and I need it in terms of y. So this is going to become x equals y squared. So when we're doing this one out, and my integral, we're doing it from 0 to 1 still. So I have 2 pi. And now my radius in this case is y. So I have y. And my height is y squared. Oh, I screwed that up actually. My height's not y squared. Why is my height not y squared? We'll see if anybody can figure out my mistake.
1 minus y squared.
Right, but why? Other than the fact that they wrote it in the problem.
Because y square is, that's like the little box area. So we need to find the distance like from 1 to y square. So it can't just be that.
Yeah, in essence, what I just did here was this part here, which wasn't the shaded part. So the shaded part's starting off at the 1 and going over. So this is what happens when I do things quick. So that's how I get the 1 minus y squared, because we're looking for the opposite side of that part. All right. So let's pull out my pi. 0 to 1, have y minus y to the third. Y. So pi y squared over 2 minus y to the fourth over 4 from 0 to 1. So I got 2 pi 1/2 minus 1/4, which is pi over 2.
Is there a reason why you wouldn't just use the disk method here?
Yeah, I wanted to show you that it was harder. This is actually the very first problem we did tonight. So this problem right here is the same as this problem. This was disk method. So I showed you a problem where you couldn't do the cylinder. You had to use the disk method. But before I even actually showed you that one, because somebody asked, I was going to show you where you could use either method, but sometimes one method's easier than the other one. And in this case, using the disk method is way easier than using the cylinder method. But they both do work, and they both do give you the exact same answer. So in that situation, either method works. It's just a method. It's a matter of which way is simpler for you to do.
But which are the cylinders? Is that I'm not getting where the cylinders are here.
This is because this box right here is completely rotated around. That's why this is the cylinder method and not the disk. The disk method is instead of like totally. When you're looking at the disk method, it's rotated around, so it makes a disk. So in this case, that bar that was going up and down is rotated around and it makes that disk. In this one, when we're looking at it, this bar, when it's rotated around, it's not going to make a disk, it's actually making that cylinder.
And so like at y equals 0.0001, the effective value of it is just the whole cylinder right there next to the x-axis.
Correct.
And it gets smaller and smaller in height as you go. Y gets up.
Yep, as y is going up, this is getting that cylinder is getting smaller and smaller. Yep.
Thank you.
All right, and that we finished section 6.2 and 6.3 tonight. So I believe next week I start chapter 7, if I remember right. I think that's all I'm doing in chapter 6. So the fun starts next week. Yep. All right, so you can do any of the problems in section 6.1, 6.2, and 6.3. So if you look here, so basically, when you look at the exercises, any of the exercise ones, I wouldn't, the further you get in the exercise, the more complicated they get. So like, don't sit there and go through and try to figure out number like 48 unless you really truly want to. It's not going to show up on the test. Most of your test problems are going to come from the beginning ones, the simpler ones here, maybe a couple of little word problems. If you want to look at some of those, that's fine. So, but yeah, if you want to practice these, that would be the best way to go. So 6.1, 6.2, and 6.3. And next week we start chapter 7, which is new ways to integrate. So it's so far all this integration has been stuff you did in Calc 1. Chapter 7 teaches you a whole bunch of new ways to integrate. All right. Any questions? The notes and the video will be posted on my website, so you can go back and review it anytime you wish.